Today we are going to present the hydrogen production and bioelectrochemical system, particularly microbial electrolysis cells. Let's start with an overview of hydrogen production. Hydrogen gas is increasingly recognized as a clean fuel source. When burned, it produces only water vapor as a byproduct, which means it eliminates the harmful emissions we associate with fossil fuels. These characteristics make hydrogen a vital component in our transition to sustainable energy system. Its versatility allows it to be utilized in various applications, including transportation and even energy storage solutions. Furthermore, hydrogen fuel cells can achieve efficiencies of around 60%, significantly higher than traditional internal combustion engines, which typically operate at only 20 to 30% efficiency. Moving on to bioelectrochemical system or BES, the history of BES dates back to 1191 when Italian physicist Luigi Galvani first observed bioelectric effects in frog legs, laying the groundwork for future studies in bioelectrochemistry. However, the modern era of BES began with Michael Porter in 1911, who demonstrated the generation of electrical current by microorganisms through the degradation of organic compounds, and this marks the inception of microbial fuel cells in the early of 20th century. Over time, researchers recognized that these systems could do more than just generate electricity. They could also produce valuable products like hydrogen gas. This realization led to the development of microbial electrolysis cells, which is the focus of our presentation today.
Moving on to the microbial electrolysis cells, it is a bioelectrochemical system that harnesses microorganisms to produce hydrogen gas from organic substrate such as wastewater or biomass. This technology generates hydrogen using less electrical energy compared to water electrolysis. Moving on to the key components, the first one is external power source. It is to provide the additional voltage required to drive the hydrogen evolution reaction. The second one is anode. It is carbon-based material to support microbial growth. For the third one is microorganism. It is the exoelectrogenic bacteria that transfer electrons to the anode during metabolism. The fourth one is the cathode. It is metallic materials to facilitate hydrogen evolution. The last one is the electrolyte. It is the medium supporting the ion conduction.
Let's dive into the core mechanisms that make MEC effective. The process begins with microbial metabolisms. MEC utilize electroactive bacteria, which are specialized microorganisms capable of metabolizing organic substrates like acetates or glucose. At the anode, these microorganisms oxidize the organic matter, breaking it down and releasing electrons and protons as byproducts. This is the foundations of the electron transfer process within the MEC. Once the electrons are released, they flow from the anode to the cathode through an external circuit, generating an electrical current. Meanwhile, the proton produced at the anode migrate to the cathode chamber. This happens via a proton exchange membrane or through the electrolyte solutions, which separates the anode and cathode chambers. This separation is critical for maintaining the electrochemical gradients needed for the next stage. At the cathode, the final steps take place: hydrogen gas evolutions. Here, the protons and electrons recombine to form molecular hydrogen gas. To drive this process, an external voltage ranging from 0.2 to 0.8 volts is applied to MEC. This additional energy is essential because the reduction of protons to hydrogens is an endothermic process, meaning it requires an energy input. By combining microbial metabolism with this applied voltage, MEC achieve efficient hydrogen productions.
Moving on, efficient hydrogen production relies on three key factors: system architecture, biological parameters, and operational parameters. In system architecture, a single chamber reactor is cost effective but produces less pure hydrogen, while a double chamber system ensures higher purity but is more complex and expensive. Next, the membrane. It separates anodic and cathodic processes, improving ion transfer and hydrogen purity. For example, Nafion, a proton exchange membrane, maintains the electrochemical gradient for efficient electron flow. Finally, the electrode design. The anode, made of high surface area materials like graphite brush, supports microbial attachment. The cathode, often platinum or nickel based, ensures high catalytic activity and resists fouling. In biological parameters, pure cultures offer controlled methane-free hydrogen but are costly. Mixed culture, like Geobacter sulfur-reducens and Shawiniella oneodensis, are stable and adaptable but prone to methane production by methanogens. To inhibit methanogens, chemical inhibitors like BESA or pre-treated electrodes can be used. Then, inoculum source. The anaerobic sludge, sediments, and agricultural residues serve as effective microbial sources. Pre-treatment, such as acid or heat, boosts microbial activity. For example, thermophilic inocula enhance yields at higher temperatures. Lastly, in operational parameters, simple substrates like acetate provide the best yield, while complex ones such as food waste or microalgae require pre-treatment for efficiency. Next, pH and temperature. An optimal pH of 6.5 to 7 supports most substrate, while a slightly acidic catholyte 5 boosts hydrogen recovery but may stress microbes. Temperature between 23 and 28 degrees Celsius is ideal for mesophilic cultures, but higher heat aids cellulose breakdown, requiring thermophilic microbes. For applied potential, the sweet spot is 0.7 volt. Exceeding 1 volt risks damaging microbes.
Greetings everyone. Moving on to the applications of MEC or MEC, they have immense potential for energy generation, environmental sustainability and resource. One of the applications is microbial electrosynthesis, where MECs produce valuable chemicals such as acetate, ethanol, or even bioplastic. They achieve this by using microorganisms to convert carbon dioxide or organic matters into complex compounds, paving the way for sustainable chemical production and carbon capture. MEC can also produce hydrogen peroxide, which is useful for water disinfection and advanced oxidation process for water treatment. Talking about water treatment, MECs can also play a significant role in wastewater treatment. They simultaneously clean wastewater by removing organic pollutants and recovering energy in the form of hydrogen or methane. This dual benefit make MEC a sustainable and cost-effective solution for industries like food processing or municipal wastewater plant. Additionally, MEC also is being explored for nutrient recovery, where essential elements such as nitrogen and phosphorus are being captured and purified from wastewater, and then they are reused as fertilizer. However, despite these remarkable applications, scaling up MEC for commercial use is challenging due to material costs, energy efficiency, and microbial stability. However, with ongoing research and innovation, MEC hold a great promise for a sustainable and energy efficient future. Thank you. Next part.
First, MECs excel at wastewater treatment. They can remove up to 88% of chemical oxygen demand from the wastewater, tackling a wide range of pollutants, even the complex organic compounds that challenge the conventional methods. So, this versatility makes MECs as a powerful tool for water saving. Moving on to the next benefit, the MECs significantly reduce our carbon footprint. They produce clean hydrogens with up to 99% lower carbon dioxide emissions than the traditional methods. Additionally, MECs support the integrations of renewable energy sources, contributing to a more sustainable energy. Let's talk about the energy efficiency. MECs are remarkably energy efficient, requiring only 0.2 to 0.8 volts of applied voltage. This is substantially lower than the conventional system, making MEC an attractive option for sustainable wastewater treatment and also clean energy. In terms of cost effectiveness, MECs have a lower energy requirements compared to the conventional method, which translates to us that it could reduce operational costs. Other than that, MEC produce hydrogen as a valuable byproduct, so these hydrogens can be used or sold, effectively offsetting our operational expenses. And lastly, MECs generate less sludge compared to the traditional system, so this means lower costs for sludge management and also disposals.
Moving on to the last part, which is the challenges and recommendations. Moving on to the last part, which is the challenges and recommendations. Moving on to the last part, which is the challenges and recommendations. Moving on to the last part.
Scaling up microbial electrolysis cells remains a critical challenge due to the gap between laboratory results and real-world pilot studies. While small-scale experiments show promise, translating these results to practical large-scale applications often reveals inconsistencies in performance and feasibility. Addressing this gap requires more rigorous pilot-scale studies to validate lab-scale findings and adapt them to industrial settings. One major challenge during scaling up is decreased efficiency as the reactor volume expands. This reduced performance is often due to issues like charge transfer limitations and uneven substrate distribution. A recommended approach is combining innovative technologies with traditional methods. For example, coupling dark fermentation with microbial electrolysis cells significantly enhances hydrogen yield. Dark fermentation not only reduces the overall energy requirement, but also provides substrates with high conductivity, which helps overcome charge transfer challenges in MECs. By integrating these processes, energy recovery and overall efficiency can be improved, making MECs more viable at larger scales. Another challenge is the limited efficiency of microbial catalysts in facilitating electron transfer. To address this, optimizing microbial catalysts through genetic engineering is, for example, strain modification and medium refinement for Shigella onidensis have shown significant improvements in current density when used as a biocatalyst. These advancements enable enhanced scalability in microbial electrochemical systems, making them better suited for industrial applications while improving overall energy recovery efficiency. Electrode material limitations also hinder MEC performance, especially at large scale. A promising solution involves simultaneously applying magnetic fields and specialized media to create artificial electroactive biofilms. This approach stimulates the growth of specific electrochemically active bacteria, leading to more evenly distributed bacterial communities and improved electron transfer efficiency. By addressing the limitations of conventional anode designs, such configurations not only enhance MEC performance but also pave the way for more innovative and cost-effective electrode materials.
In conclusion, microbial electrolysis cells present a promising bioelectrochemical technology for sustainable hydrogen production, wastewater treatment, and resource recovery. Despite their benefits, challenges such as upscaling, microbial efficiency, and electrode limitations hinder widespread applications. Continued research and technological advancement are essential to enhance performance, cost effectiveness, and integration into existing energy systems. Thank you very much.